Hello everybody and welcome to example 2. We are looking at the top of page 35 in the workbook here, and this example is going to lead us into the concept of the differential of a function, a way of approximating the amount of change that we're getting in a function. Right, so let's read this example together. It describes a situation that we've talked about before. In a room, the temperature is given by capital T equals f of x and little t degrees Celsius, where x is the distance from a heater and t is the elapsed time in minutes since the heat has been turned on. Okay, and we're going to suppose that a person is standing 3 meters from the heater 5 minutes after it has been turned on. Okay, so before we read farther here, let's start drawing a picture just to help us visualize the situation that we've got here. Okay, so we've got two input variables, x, okay, which is the distance away from the heater, and t, which is the time in minutes. Okay, can I sneak the units in there? Meters. Okay, I'd like to have the units here. That makes it a little easier to think about. Okay, so x in meters. All right, so our starting position is we're 3 meters away from the heater after 5 minutes. So that would be on this picture that we're drawing, the point 3,5. Okay, that's where we're starting. Okay, and here's what we're observing. The person who's standing there. Number one, the temperature is increasing by 1.2 degrees Celsius per minute. That's how fast the heater is warming up this room at that position. And number two, walking away from the heater, the temperature decreases by 2 degrees Celsius per meter as time is held constant. So we're going to get colder as we walk away from the heater. That's what that's telling us. Okay, here's what we're being asked to estimate. How much cooler or warmer would it be 2.5 meters away from the heater after 6 minutes? Okay, that's describing a new point on this diagram for us, maybe about right here, 2.5 and 6. And we're simply being asked to estimate how much would the temperature change if we move between those 2 points. Okay, now what's kind of interesting about this is we can sort of describe the temperature change as part of a two-part process. Okay, so to get between these 2 points, the first thing we need to do is to move in the x direction. We need to move back towards the heater. I'm going to call that distance that we move delta x. And then we need to go forward in time, 1 minute from 5 to 6. I'm going to call that change in time delta t. Okay, what we're going to do is to ask ourselves, can we estimate the temperature change along each of those two dotted paths, basically, that we wrote down? Okay, so just notationally, I'm going to let delta t be the change in temperature between those 2 points. Okay, and we'll try to describe that change in temperature in 2 pieces. Okay, so delta t is approximately... Okay, I want to be careful with space here. Okay, I'm going to deliberately leave a little bit of space up at the top because there's something that we're going to write in kind of in the process of doing this. All right, so let's first talk about the first part of our path. Okay, so moving along this delta x portion of the path. Okay, so how much would the temperature change if we move from a distance of 3 meters from the heater to a distance of 2.5 meters from the heater? Well, to answer that question, we need some information about how fast the temperature is changing as we move closer to the heater. And that rate of change is kind of contained in this piece of information, the 2 degrees Celsius per meter. That's the amount by which the temperature decreases as we move away from the heater. So I'm going to start with that number. Minus 2 degrees Celsius per meter. And that rate is going to get multiplied by the distance that we moved. Okay, so how big was delta x? Well, it was 0.5, but it's actually negative because we moved closer to the heater. Okay, so negative 0.5 meters describes our change in distance. Okay, if you take those two things and multiply them, Okay, notice first that the meters cancel, so we're going to get degrees Celsius. And -2 times -5 is 1 degree Celsius. If we've done everything right, that would be saying that the temperature should be increasing by 1 degree Celsius. Okay, does that make sense? So if we move from a position of 3 meters from the heater to 2.5, should it get warmer? It should. Okay, so getting positive 1 degree Celsius, at least the sign makes sense. Okay, so far what we've done is approximated the temperature change as we take that step, that half-meter step closer to the heater. Now we're ready to explore the question of how much would the temperature change if we go forward in time from 5 to 6? Okay? Well, to measure that temperature change, we need some information about how fast the temperature is changing as time goes forward. And that's contained in this number, which tells us that the temperature is increasing by 1.2 degrees Celsius per minute. So we'll start with that number per minute. And then the question is, how many minutes go by if we go from 5 minutes to 6 minutes? Well, that's a change in time of 1 minute. Okay, so we'll multiply those. Notice that the units cancel. And if we take 1.2 times 1, we're going to get 1.2 degrees Celsius. And again, we can ask ourselves, does it make sense that we get a positive number there? And it does, because as time goes on, this heater is going to warm up the room, so it makes sense that we should get a temperature increase. Okay, and so add those two numbers together, and we get our approximate temperature change, which would be 2.2. Okay, and so the answer to our question, okay, if we just write a brief sentence here, we therefore see that the temperature increases by about 2.2 degrees Celsius. Okay. So good, we've got an answer to our question, but what's interesting is to analyze the pieces in that answer. Okay, kind of look at the building blocks of how we got to 2.2. Okay, so if you start with this -2 degrees Celsius per meter, that was a rate of change, and it was a rate of change in the x direction, how fast the temperature is changing as we move away from the heater. So that was Fx at 3.5. Okay, if we want to use our partial derivative notation. Okay, and then the -0.5, that was the distance that we moved in the x direction. I'm going to call that delta x. We multiplied those two numbers and got the temperature change due to moving closer to the heater. Okay, and then moving over to the 1.2 degrees Celsius per minute, that's also a rate of change, but it's the rate of change with respect to time as time goes forward. Okay, and we took that number and we multiplied by the amount of time that changed, going from 5 to 6 minutes, so that was delta T. And so our change in temperature approximation that we came up with was made up of those four numbers. Okay, and we can generalize that by looking at this definition below, the differential of a function. That's really what we calculated in example 2. The differential of a function is given by this formula. df equals the derivative in the x direction times dx plus the derivative in the y direction times dy, and this represents the approximate change in our function. Just like what we did in example 2, we measured the approximate change in temperature. We can use that method to find the approximate change in any function. Now, the only thing to notice here is that the notation is a bit different in this. Instead of writing deltas, we're writing d's. So this df that you see here, it's like the delta t that we did in example 2. It's the change in f. And then similarly, dx and dy, those are like the delta x and the delta t. Okay, they're just changes in x and y. Okay, and that's what's being kind of explained to you in the sentence down here. Conceptually, df represents the approximate change in the output values of f if x is changed by dx and y is changed by dy. Okay, and so in future examples, we'll dig a little bit deeper into this differential and see what we can do with it to approximate function changes.